Hi everyone! In this video we study mechanisms for the reactions of alcohols with thionyl chloride and phosphorus tribromide. These two conditions yield alkyl chlorides or bromides from primary or secondary alcohols. And these reactions proceed with inversion of configuration. It's important to note that tertiary alcohols do not react under these conditions. And based on these data, we do not expect a carbocation intermediate in our mechanism. If we did, we would see mixed stereochemistry in our products, and our conditions are neutral, which do not favor the formation of such a strong electrophile. Substitution reactions require good leaving groups, so that's something to keep in mind as we begin to sort out our mechanism. The OH group as it is now would leave as OH-, which is a strong base, a poor leaving group. So before we start pushing arrows, let's get a structure drawn for SOCl2, thionyl chloride. Sulfur will be our central atom because it is the least electronegative element out of S, O, and Cl. That means the O and Cl's will be attached to that central atom in such a way. We can add in our lone pairs, the remaining electrons, if we added them all up. And what we would find is we need to have a second bond between the oxygen and sulfur to be sure that all of the octets are satisfied. Now that we have the structures of our two reactants, can you predict which atom will be the electrophilic site? In order to identify electrophilic sites, we want to look at the bond dipoles. And what we see in thionyl chloride is that the sulfur atom has 3 electronegative atoms attached to it. And these electronegative atoms are going to be pulling electron density away from that sulfur atom, creating that partial positive charge that is characteristic of an electrophile. In addition to looking at the bond dipoles, we can also draw a resonance contributor that shows the sulfur atom is electron deficient. And as such, we would predict the sulfur atom to be the electrophilic site in thionyl chloride. Now we're ready to push arrows. The electrophilic sulfur will accept electrons from the nucleophilic oxygen atom. And to make room for that new bond, the oxygen-sulfur pi bond will break. This gives a new sulfur-oxygen bond. Nothing has changed with the configuration at the carbon just yet. At this point, we are going to generate chloride ion, and the oxygen electrons will form a second bond to sulfur and kick out the chlorine atom. This is a very common pattern that you'll see in mechanisms. Remember, we have pyridine in this reaction, and pyridine is the best base. It's a weak base, but much better base than chloride. Can deprotonate this oxonium ion. Finally, we have a good leaving group. This species is going to be a weak base, good leaving group. So the chloride ion can come in from the opposite side and displace that leaving group. This gives our alkyl chloride, as well as the leaving group. And this leaving group will decompose, much like carbonic acid in water decomposes to CO2, and water will yield SO2, a gas that bubbles out of the solution, and the chloride ion. We started this reaction by making OH a good leaving group with a nucleophilic substitution on the sulfur atom, at which point the chloride ion can displace the chlorosulfite group to produce our alkyl chloride via an SN2 mechanism. This explains the stereoselectivity as well as the fact that tertiary alcohols do not undergo this type of reaction. The phosphorus tribromide reaction proceeds in a very similar manner, though in this example, phosphorus is our electrophilic site. So the oxygen nucleophile will attack the phosphorus atom and displace a bromine. This forms a new phosphorus-oxygen bond, which is quite strong, as well as generating the bromide ion that can be used in our next step. This species we have created now is a good leaving group. It will leave as a neutral compound. So as Br- comes in from the back side, can displace that leaving group, giving us overall inversion of configuration, as well as our neutral leaving group. These reactions proceed to give alkyl halides from alcohols. We first must make the hydroxyl group a good leaving group via a nucleophilic substitution, either at sulfur or phosphorus, depending on what the reagent may be. And then a second step is the SN2 displacement of that good leaving group. Thanks for watching.